So we've talked about how to take the derivative of the ln function. Now let's talk about what we have to integrate to get back to the ln function. So here's what we know. We know if we take the derivative with respect to x of the ln of x, we said that was going to be 1 over x. And that works when x is greater than 0. This is the domain restriction on the ln function. So if we wanted to go backwards, then we would want to integrate the 1 over x function. Well, if we integrate something we want to differentiate, then we should end up with this guy. So if we integrate 1 over x with respect to x, then we should get the ln of x, the function, plus some constant of integration. However, remember that domain restriction. So if for this to work, we have to restrict x to be greater than 0. Remember, the ln has some domain restriction issues, and whatever we integrate has to have the same domain as what we get. Those domains have to match, in other words. So that absolute value will ensure us that whatever we're taking the ln of will always be greater than 0. So that's where our log rule is going to come from. If we integrate 1 over x dx, we're going to get the ln of the absolute value of x plus c. That absolute value is very important because it keeps that domain restriction from that derivative to the integral. So likewise, if we did a u substitution, it's going to work the same way. It's going to be the ln of the absolute value of u plus c. And that gives us enough information to be able to derive our trig integrals. We already know how to integrate sine and cosine, but we can derive the other 4. How do we integrate tangent, cotangent, secant, and cosecant? And it actually comes from this ln process. So just for fun, let's look at 1 or 2 of those. Let's integrate the cosine function. Or not cosine, cotangent. So let's do a proof. We want to integrate the cotangent of x. And then on the last page, they told us that if we integrate cotangent, we're going to get the ln of the sine. So I'm going to show you where that's coming from. So we know if we integrate cotangent, cotangent is the same thing as cosine over sine. And we can look at this as 1 over sine of x times the cosine of x dx. So let's do our u substitution from the last chapter. If we let u be that denominator, sine of x, then du, derivative of the sine, is cosine, and we took that derivative with respect to x. So then if we do a rewrite, we're going to have 1 over u, and all of this would become du. And then this becomes the ln of u plus some constant of integration. So then if we sub back in, this was the integration step. If we sub back in, we're going to have the ln of the sine of x plus c. So you can see if we integrate that, we will get that, all because we're doing that substitution for cotangent, which is cosine over sine. Let's do another one. Let's integrate secant of u du. And we're going to prove that if we integrate secant, we're going to get the ln of the secant plus the tangent. This one's not as obvious, so we want to prove this. Integrating secant of x dx is equal to the ln of secant of x plus tangent of x. Notice the absolute value there, that's important. And then plus c. So that's what we want to prove. So we're going to start by saying we want to integrate the secant of x dx. Well, one thing we can do is we can multiply the top and bottom of a fraction by something. As long as we do the same thing, we're multiplying by 1. So let's multiply by secant of x plus tangent of x. So notice we have not changed the domain restriction here. Secant's the same thing as 1 over cosine. So cosine's in the denominator. Cosine's in the denominator here and here. So that domain has not changed. That's important. We can't change domains. So then now we have secant squared of x plus secant of x tangent of x all over secant of x plus tangent of x dx. So let's do a u substitution. Let's let u be that denominator, secant of x plus tangent of x. So then the derivative of the secant is secant tangent. The derivative of the tangent is secant squared. And then we need to show we took that derivative with respect to x. So you can see where these pieces are coming from. It comes from taking the derivative of that denominator. So then if we do our substitution, we have all the pieces. All that top is our du. That bottom is u, and we're integrating that. And then when we integrate du over u, we get the ln of the absolute value of u plus c. So then when we sub back in, we're going to get the ln of the absolute value of secant of x plus tangent of x plus c. So that's what we wanted to prove. So you can see how this guy becomes this. We did have to use this trick to help get us there. It's not as straightforward as the last one. So now that we've proven these and we've talked about how to integrate to get the ln function, let's do a few. So let's look at number 5. We could pull that 5 out. So it's 5 times the integral of 1 over x dx. And when we integrate 1 over x dx, we're going to get the ln of the absolute value of x plus c. So there's our final answer. If we look at 7, we have 1 over 2x plus 5 we're trying to integrate. So think about your u substitutions. If we let u be that denominator, 2x plus 5, then the derivative of that is 2 dx. Okay, let's check out what we have. Notice we're missing that 2 in here. We can multiply it in as long as we compensate with a 1/2 in the problem. So then our rewrite, we have that 1/2 out front that we had to compensate with. Now we have that 2 dx on the top, so that's all of du. And then that 2x plus 5 is our u. So then when we integrate, we're going to have 1/2 ln absolute value of u plus c. And then if we sub back in, we're going to have 1/2 ln absolute value 2x plus 5 plus c. So there's our final answer. That's our derivative. So some of these are going to require a u substitution. Let's look at 9. 9, we're integrating x over x squared minus 3 dx. So think about a u substitution. Let's let u be that denominator, x squared minus 3. So du is 2x dx. Okay, let's see what we have. So we have the x and the dx, but we're missing that 2. We can multiply it in as long as we compensate with a 1/2. So now if we do a rewrite, we have 1/2 times the integral of du over u. Every piece is used here. All of this is our du. That denominator is our u. So if we integrate, we have 1/2 ln of u, absolute value, plus c. And then if we sub back in, 1/2 ln absolute value x squared minus 3 plus c. So there's our final answer. We would say this is equal to y prime to make a complete sentence. Actually, we don't need that here since they're just giving us an expression. So keep in mind that u substitution is going to come back. Let's look at 11. Let's try letting u be that denominator. U is x to the 4th plus 3x. So du would be the derivative, which is 4x cubed plus 3 dx. So if we go over here to the problem, that's all of our du. So if we rewrite this, we have everything we need. So this is in the form of du over u. When we integrate, this is the ln of the absolute value of u plus c. And then when we sub back in, it's the ln of x to the 4th plus 3x plus c. So there's our final answer. So let's take a look at 13. Let's make it a little bit more interesting. We are integrating x squared minus 7 over 7x dx. Okay, we can split that numerator and we can think about that as x squared over 7x minus 7 over 7x dx. So then we can rewrite this first one. Notice the x's are going to reduce. So we have an x in the top and a 7 in the bottom. And the 7's are going to reduce here. So that's just 1 over x dx. Now keep in mind, all of that is in understood parentheses there. Now, I'm going to split this into 2 different integrals. And the reason I would want to do that is because I can pull that 1/7 out, but I can only pull it out of the first piece. I cannot pull it out of the second piece easily. And then now we can integrate each piece. When we integrate x, we're going to have x squared over 2. When we integrate 1 over x, it's the ln of the absolute value of x plus c. And then clean it up. So we have x squared over 14 minus the ln of the absolute value of x plus c. So there's our final answer. Let's look at 15. So that next one, we're integrating x squared plus 2x plus 3 over x cubed plus 3x squared plus 9x dx. You always want to start with saying, what if I let u be that denominator? Does that help me? Sometimes integration is just playing with it until you get it. Well, if we let it be the denominator, what would our du be? So our derivative would be 3x squared plus 6x plus 9. Is that anything close to what we have in that top? Well, if we were to factor a 3 out of that du, we see that we have this piece and we have the dx. We're just missing that 3. So we can multiply everything by 3 as long as we compensate with a 1/3 somewhere in the problem. So now that we know that, let's do our rewrite. So we have 1/3. We've already compensated. We've multiplied by 3 and compensated for that. So now everything in the top is our du and everything in the bottom is our u. So now this guy's easy to deal with. If we integrate, it's 1/3 ln absolute value of u plus c. And then if we sub back in, we have 1/3 ln absolute value x cubed plus 3x squared plus 9x plus c. So there's our final answer. So the next two problems are going to be a little bit more interesting. 17, we have x squared minus 3x plus 2 over x plus 1. Notice the degree of the top is bigger than the degree of the bottom. So let's do some long division. That's going to make this much easier to deal with. So we have x plus 1 in the bottom, x squared minus 3x plus 2 in the top. Long division is one of our tricks. Anytime you have the degree of the top bigger than the degree of the bottom, do long division and then it will make it easier. And usually what will happen is you'll end up with a piece that will be a polynomial piece, and then you'll end up with something that will turn into an ln. So if we do long division here, x goes into x squared x times. We're going to multiply back through. So this is x squared plus x. And then we're going to subtract. So those x squareds cancel. Negative 3x minus x is a negative 4x. And then we're going to bring that 2 down. And then we repeat the process. X goes into negative 4x, negative 4 times. Multiply back through. Negative 4 times x is a negative 4x. Negative 4 times a 1 is a negative 4. We're subtracting. Negative 4x minus negative 4x will cancel. 2 minus negative 4 is a positive 6. Remember, this guy's the remainder. So then if we were to rewrite this, this is equivalent to writing x minus 4. So that the denominator goes into that numerator, x minus 4 times. And then we have a remainder of 6 out of the x plus 1 left. So then when we integrate this, remember there's an understood parentheses there. When we integrate this, we could think about integrating each of these pieces separately. I'm going to think about that polynomial piece. And then I'm going to integrate that 6 over x plus 1. Okay, notice I have not integrated anything yet. I have rewritten the problem to make it a little bit easier. And then I'm going to pull that 6 out of that second one. So now when we integrate, this is going to be x squared over 2 minus 4x. And then over here, think about a u substitution. So I'm going to write it off to the side. So if we let u be x plus 1, then du would be 1 dx. So all of that is du. This is u. So we're integrating 1 over u du, which is going to be the ln of u, which is going to be the ln of x plus 1. So that's what I'm thinking when I do this. So that's going to be the ln of x plus 1. And then we have a plus c. So notice that I just put the plus c at the end here. You could have said, and I'll do this in red, you could have said x squared over 2 minus 4x plus some constant here. And then if you would have done the integration here, you would have another constant. But if I take a number and add a number to it, I'm going to get one number. So instead of having two constants there, we can combine those into one. And this is a little bit cleaner to look at than that second guy. So that's why we would do that. And let's look at one more. Let's look at number 30. We are integrating 4 over 1 plus the square root of 5x dx. So this is going to require some substitutions. Here's what I would want to try to do. I would say, let's let u be that whole denominator and let's see what happens. So if that's u, then let's take the derivative. We need du. The derivative of 1 is 0. If we take the derivative of this, we have to think about how we would rewrite that square root of 5x. And it would be that. 5x to the 1/2. So we would bring down the exponent. Then subtract 1 from the exponent. And then take the derivative of the inside. So if I clean that up, I have a 5 in the top. I have a 2 square root of 5x in the bottom. And we took that derivative with respect to x. So then I'm going to rewrite that. So we have u is equal to 5 over 2 square root of 5x times dx. So I'm going to box in everything we have so far. So we have something for u. And then we have something for du. So right now we have a 4 over u, but we need something to substitute in for this dx. That's where this guy's going to come in. If we were to, let's get dx by itself and multiply everything by that reciprocal. So if we do that here, that's going to give us a substitution for dx. So if we solve for dx, we would multiply by 2 square root of 5x over 5. What we do to one side, we would want to do on the other. Math is always fair. So you can see how this fraction would cancel with this fraction, and we would have dx. And then we have 2 square root of 5x over 5 times du. So here's the problem. We have x's and u's mixed up. We really need a substitution for that square root of 5x. So if we do that, I'm going to go back up here. Okay, notice we could take this guy and we can solve it for the square root of 5x just by moving that 1 over. So we have u minus 1 is equal to the square root of 5x. So we have a lot of substitutions going on in this one particular problem. So let's recap. We started by saying, what if I let the denominator be u? Well, once we pick u, then we have to find du. So we found du by taking the derivative of this. Okay, so then we went back to the problem. What do we have? Well, we have something for u, but we don't have anything for this dx. Everything has to be in one variable up here. So that's where we took this derivative of u, du, and we solved it for dx. So we multiplied both sides by the reciprocal, And when we did that, we got dx by itself. So now we have something for x, but we have u's and x's in here. We need a substitution for that. So then if we substitute in there, that square root of x, a square root of 5x is equal to u minus 1. So there's the substitution that we need. You can see the process we had to go to get to that. So now we can do our substitutions. So that 4 is still there. All of this in the denominator we called u. And dx is equal to 2 times u minus 1 over 5 times du. Now, let's clean all this up. This is going to be 8 times u minus 1 over 5u times du. I'm going to pull that 8/5 out. So now we have u minus 1 over u times du. And we can use some of those tricks we did before. Let's split that denominator to make this just a little bit easier. So if we do that, we now have 1 minus 1 over u times du. Remember, there's no understood parentheses there. So we can integrate each of those pieces separately. So we have 8 over 5 times. When we integrate 1 with respect to u, we're going to get u. When we integrate 1 over u, it's going to be the ln of the absolute value of u. And then we have a plus c. Now let's sub back in for u. We said in the beginning u was equal to 1 plus square root of 5x. So there's our final answer. So you can see all the substitutions it took to get us to that point. Sometimes integration is about playing with it and seeing what you can do, picking something for you, see if it works. And with this one, picking that denominator for you works out pretty well for us. And in fact, if we wanted to, we could simplify this guy just a little bit more. If you have to take differential equations, you'll see this come up. We simplify a lot in there. So check out what's going to happen. I'm going to distribute that 8 over 5. So notice we have an 8/5 here, plus some number on the end here. We know a number plus a number is just a number. So if we wanted to, we could even write this like this, combining those two numbers together. Call it some other number. You can call it C. I'm used to calling it a different constant, C1. WebAssign is going to force you to use a C, not a C1, I believe, in this course. But you can see how we can combine those constants together. That's going to come up a lot in other courses down the road.